예, 안녕하세요. 저는 화학공학과 이준혁 교수님 실험실에서 학위파견으로 박사과정을 하고 있는 이희동입니다. 현재 저는 LG 디스플레이에서 모바일 OLED 소자 개발팀장 역할을 수행하고 있고, 현재 파트타임으로 코스웍을 진행하고 있습니다. 금일 제가 보고 드릴 내용은 현재 제가 관심 있고 특히 중요한 모바일 OLED 소자에서 블루에 대한 성능 향상에 맞추어 현재까지 개발된 스터디에 대해서 연구를 하고, 그 컨셉 중에 향후에 셀렉다운해서 미래 연구를 진행할 예정입니다. 동기입니다. 모티베이션은 이제 먼저 OLED 디스플레이에 대한 트렌드를 먼저 말씀드리고, 왜 블루의 효율이 중요한지에 대해서 말씀을 드리겠습니다. 두 번째는 OLED 디바이스, 특히 블루에서 커런트 테크놀로지에 대해서 말씀을 드리겠습니다. 블루 인강과 블루 TADF, 블루 하이퍼플러센스에 대한 기술에 대해서 말씀을 드리고, 현재 각 기술에 대한 이슈 사항과 그걸 극복하기 위한 스터디 내용을 말씀을 드리겠습니다. 마지막으로 서머리 순으로 말씀을 드리겠습니다. 발표는 영어로 진행을 하도록 하겠습니다. Recently, the display industry is going to replace liquid crystal display with organic lighting emitting diode. Customers' needs is light, thin form factor, and mobile communication is going to transfer 4G to 5G, which means 5G is 20 times faster than 4G. Therefore, 5G users get many information and take advantage of opportunity compared to the 4G users. In terms of display performance, power consumption is most important to meet performance for 5G mobile display. Especially, high efficiency blue device is most important to reduce power consumption because of that external quantum efficiency EQE of blue is very low compared to the other color, red and green. That's why blue device is using blue device is using fluorescence material, otherwise red and green is using phosphorescence materials. In point of view, device structure, total thickness of OLED device is about several hundred nanometer thickness, composed with more than 10 layers, which means it is nano vapor deposition process having sensitivity variation. Therefore, there have been several studies to develop high efficiency blue devices such as Summer activated delayed phosphorescence blue, hyperfluorescence blue. Organic lighting emitting diode material is fluorescence, which was first OLED material. Fluorescence OLEDs were an innovation because it is easy to synthesize and have a flexibility compared to the inorganic lighting emitting diodes. But the internal quantum efficiency are only 25% according to electron spin statistics. Excited electrons can generate 25% of a singlet and 75% of a triplet. In fluorescence OLED, triplet excitrons are wasted by non-radiative relaxation. That's why the scientists developed the phosphorescence OLED, which have 100% of internal quantum efficiency. In this slide, I would like to show the comparison of current technology, such as fluorescence, TIDF, phosphorescence. Firstly, I want to talk about the blue phosphorescence material. Blue phosphorescence, the second generation of OLEDs, pH OLEDs have heavy metal atoms like platinum, iridium. Those have atoms make large spin orbit coupling, which can able to utilize both singlet and triplet excitons for emission due to the enhanced intersystem crossing. So it can approach to 100% for internal quantum efficiency. But there is a demerit. First of all, the heavy metal atoms are high-cost materials, also due to their high emission energy and few microseconds long exciton lifetimes. It generated hot excitons which enhanced the degradation of emitting layer. Although the triplet exciton lifetime is greatly reduced recently, it is still much longer than the singlet lifetime, about nanosecond. Long exciton lifetimes accumulate triplet annihilation or triplet Polaron annihilation in high current densities. In blue phosphorescence OLED involved the energy of two triplet statics fusing together, resulting in an energy exciting in a higher excited state, which caused low efficiency. In research, for blue phosphorescence material OLED, when triplet excitons combined with Polaron, it created hot excited state which are larger than the bond dissociation energy. This effect is so-called roll-off, generally occurred in high luminescence. So the device lifetime, the most important issue is phosphorescence blue devices. Secondly, I want to talk about the TIDF materials. TIDF is a thermally activated delayed process. In 2010, Adachi and their co-work has developed the third generation OLED, which was called thermally activated delayed process. The requirement of TIDF materials is a small energy gap, delta ESD, between singlet and triplet, about 0.2 electron voltage. When delta ESD is small enough for the reverse intersystem crossing, RISC, the exciton in the T1 state can be efficiently convergent into the S1 state by room temperatures, followed by radiative fluorescence. This means that internal quantum efficiency of TIDF will be 100%. There is a merit that TIDF is inexpensive compared to the phosphorus OLED, since the former comprises purely organic molecules which are relatively cheap. But the problem is the small singular triplet energy gap, delta EST, and the high radiative fluorescence rate always force the concentration. In generally, donor and acceptor systems with twisted geometry are mainly adopted to achieve spatial separation between the HOMO and LUMO and minimize the exchange integral between these orbitals, resulting in small delta ESD. But molecular orbital separation between HOMO and LUMO, lower molecular oscillation strengths, which are related to photoluminescence quantum field. Therefore, the selection of a proper donor and acceptor unit is important for designing functional TIDF materials. Also, because of donor-acceptor structures, when the TIDF molecule excited, there will be various excited energy states, causing wide pull width and half maximum. In other words, color purity is very poor. Additionally, TIDF also use triplet exciton, which occur TTA and TPA, causing roll-off. Thirdly, I want to talk about blue hyperfluorescence. The blue TIDF always achieved high external quantum efficiency, but the spectrum of efficiency emission is relatively broad, which means color purity is bad. To solve this problem, researchers developed a hyperprocessor system in which TIDF materials work as an assistant dopant to increase the efficiency of transfer of exciton from assistant dopant to fluorescence emitter. The concentration of dopant material is lower than 1%, avoid exciton formation in dopant material, and to prevent triplet energy transfer from TIDF to the dopant material. The three molecules, the host TIDF molecule and the fluorescence, are in charge of carrier transport, exciton formation, and photoemission, respectively. Compared to the blue phosphorus OLED, TIDF exhibit flexibility in molecular design without heavy metal atoms. Also, the efficiency and color coordinate are good. The merit of blue hyperfluorescence exists. First, the host material should have a high singlet energy, which causes the full lifetime. Also, the energy transfer cannot perfectly happen. There should be loss processing in hyperprocessor system. Yes, and this is the second agenda current. I would like to talk current technology. Firstly, I want to talk about the TADF synthesize for blue devices. One of the most efficient singlet exciton harvesting approaches for fluorescence OLED is to introduce TADF emitters as assist dopants or synthesized to harvest the singlet exciton of fluorescence emitter by mainly the first energy transfer process, which is also called hyperfluorescence. In this approach, the role of TADF assist dopant, which is called synthesized in this work, is to upconvert triple excitons into single exciton and to transfer the single exciton energy to the fluorescence emitter. The emitting layer is made up of host, TADF synthesizer, and fluorescence emitter. The host material is required to have a higher singlet triplet energy than TADF synthesizer and fluorescence emitting to prevent reverse energy transfer. The TADF material should have a faster reverse intersystem crossing rate from triplet excited state to singlet excited state to suppress Dexter energy transfer and emission wavelengths overlapped with the observed wavelength range of the fluorescence emitter for efficient post-energy transfer. The fluorescence emitter should have a high PL quantum yield for high external quantum efficiency, a small Stokes shift for efficient energy transfer, and pure emission color. Moreover, the HOMO and LUMO of TADF synthesizer and fluorescence emitter should be well aligned to minimize carrier trapping by the fluorescence emitter. In device structures, the TADF synthesizer highly doped, while the fluorescence emitter is highly doped to avoid efficiency loss process like Dexter energy transfer and charge trapped by the fluorescence emitter. The merit of TADF synthesizer fluorescent are high EQE, pure emission color compared to the TADF due to the sharp emission spectrum of the fluorescence emitter, and the long device lifetime compared to the TADF due to the stability of fluorescence emitter. Secondly, in this slide show Exciteplex synthesized fluorescence OLED. Another method of harvesting singlet excitons of fluorescence emitter is to use an Exciteplex host and intermolecular complex of donor and acceptor type materials that display the TADF property. The Exciteplex are formed by complexation of two materials driven by their large HOMO and LUMO offset. Such Exciteplex is showed TADF features when the HOMO and LUMO offset is large, but they do not exhibit TADF characteristics if the HOMO and LUMO offset is not sufficient. The TADF properties of the Exciteplex processes are important for synthesizing effect because of upconversion of triplet exciton into singlet exciton is essential to synthesize the singlet emission of the fluorescence emitter. Therefore, only TADF type exciteflexes that have a small delta ESD were employed as the synthesizer to improve the external quantum efficiency of fluorescence emitters. There have been many TADF exciteflexes that show triplet exciton to singlet excitons convergence of singlet emission. Among these exciteflexes, several exciteflexes were used to synthesize singlet emission of fluorescence emitter. This slide shows the hyperfluorescence OLED. The blue TADF OLEDs achieved high external quantum efficiency, but the spectrum of emission is relatively broad, which means color purity is bad. To solve this problem, the researcher developed a hyperfluorescence system in which TADF materials work as an assistant dopant to increase efficiency of transfer of exciton from assistant dopant to fluorescence emitter. The concentration of dopant material is lower than 1% to avoid exciton formation in the dopant material, and to prevent triplet energy transfer from the TADF to dopant material. This slide shows about the device structure for lifetime in blue devices. In this slide shows mixed host structure and graded doping of emission layer. The most effective ways of adjusting the emission zone is to mix the hole type and electron type host material together. Although the bipolar host and the thermally activated delayed fluorescence type host can control the emission zone, a mixed host is even better than a bipolar host because various combinations can be easily accessed. Unfortunately, no stable mixed host for blue triplet emitters was demonstrated. However, there have been several examples in red and green phosphorescence OLED wherein the mixed host improved lifetime by reduced TTA degradation process. Therefore, the mixed host concept may also work well as a TTA managing method in blue phosphorescence OLED. Both an exciteflex type mixed host and exciteflex-free type mixed host might be useful as a TTA managing host. The mixed host can also be an efficient TPA managing method of phosphorescence OLED devices. Mixing the two host materials balanced the carrier in the emitting layer, which reduced the number of positive and or negative polaron in emitting layer because of most polaron can form the excitons. In the exciteflex type mixed host devices, the lifetime of mixed host devices significantly increased compared to that of singlet host devices. Even though the energy transfer from the exciplex host to the emitter improved the lifetime of devices, the underlying mechanism was actually a reduction in TPA because of fluoron was less likely to exist in the emitter because charge trapping was not likely in emitting layer. Doping of a Hall transfer or electron transfer layer which are with a low triplet energy material were also useful to reduce TPA in advance. The idea of a strategy was to reduce the number of triplet exciton which would decrease TPA degradation. The device concept was experimentally supported by observed increases in lifetime in the phosphorus OLED devices. As explained above, the decrease in lifetime due to TTA and TPA process are associated with a triplet exciton and fluoron distribution in the emitting layer. Currently, the mixed host and graded doping structure are effective device approaches to reduce TTA and TPA. However, current device approaches cannot fully resolve the TTA and TPA degradation of phosphorus OLED devices. Therefore, other devices approaches to manage the TTA and TPA at the same time are required. The device's concept used to manipulate the TTA and TPA processes is shown in the figure as below. In this slide is about the carrier balance for the lifetime. The study of carrier balance have identified the change in the carrier balance as the main degradation process. The EL spectra change in the TADF emitters occurred during degradation testing and occurrence electron emission from HBL indicated that degradation of electron transferability of the EML accelerated device degradation, and focused on the degradation phenomena of OLED that are based on sky blue thermally activated delayed fluorescence emitter, and clarifies the degradation mechanism based on spectral change of electroluminescence, which indicated the form of electron emission from the electron transfer layer. Additionally, it is determined that the change in the carrier balance that occur during the degradation process can be ascribed to the formation of electron trap. This is in terms of the TADF materials. In this slide shows the stable host material for TADF material. The host material generally play a vital role in forming the excitons that will be transferred to emitter. Host also played as an external harvesting material in the emitting layer for emitters by blocking external quenching of the emitters. This is the reason why the emitters are uniformly distributed in the host to inhibit triplet external quenching. In the luminescence process, the hole and electrons are predominantly transported by the host in the emitting layer to generate external dominantly in the host and deliver to the external energy to the triplet emitter. Therefore, the external formation is dominated by the host. For example, in case of emission of phosphorus mechanism, the main external generation in the host followed by energy transfer to the triplet emitter in the luminescence process indicated that the host is one of the most important material to determine the external quantum efficiency and the lifetime of the phosphorus OLED. Among the recent studies about lifetime degradation, the bond dissociation energy calculation is dealt with as important factors concerning lifetime. Of course, material properties of the host itself is important for degradation. However, energy transfer mechanism is also important because of the real emitting materials are emitters. In summary, blue efficiency is the most important to reduce power consumption for OLED display. Current study is focused on TADF materials, not having heavy materials, atom-like phosphorus blue material. TADF blue devices have a merit of OLED efficiency, otherwise, lifetime is not so good. It is needed to increase lifetime for TADF blue devices through carrier balance optimization, adopting the high bond dissociation energy material, and new device structure. The material development strategy suggested above should be combined with a device strategy to suppress degradation processes such as triplet annihilation TTA and triplet polaron annihilation TPA. For example, a graded doping structure, stepwise doping structure, interface exciteplex structure, and host exciton managing structure can be employed for further extension of the lifetime of the TADF host-based phosphorus OLED and TADF OLED. Considering that the history of TADF materials developed is only 7 years, the advance of the external quantum efficiency and lifetime of the TADF-based OLED was remarkable, and further exploration of the materials and the device structure would enable the commercialization for the intramolecular type TADF materials as well as the intermolecular type TADF host. Thank you for attention.